Hello students, in today's session we shall discuss the lattice or space lattice in solid state lesson. Lattice or space lattice, it is just nothing but the periodic arrangement of the points. You just keep the points in a periodic arrangement. The environment around each point must be same. See here, these points are arranged in a sequence manner, periodic arrangement. The pattern is same in all these cases. This direction or this direction, you go in any direction, the arrangement of the particles is same. No need to consider these points as atoms or molecules or ions. You can take as a bricks also. If you keep the bricks in a periodic arrangement, that arrangement is also called as a lattice. So space lattice or lattice tells only about the arrangement of the points. It will not tell anything about the crystal lattice. A crystal lattice is different from the space lattice. If these points are replaced by the atoms or molecules or ions, such type of the lattice is called as the crystal lattice. If these points are occupied by the bricks or any something else, it is simply called as the lattice. So in lattice, the arrangement of the particles must be in a regular pattern, so that the environment around each particle must be same. Here you can see, let us consider these particular atoms or these particular points. Imagine the distance between the 2 points is a unit distance, 1 centimeter or 1 meter, you can consider it. So the distance from here to here is 1 and from here to here is 1, and along this direction it is root 2 and along this direction it is root 5, and the same thing can be observed even here also. Here also, if you take the points from here to here, it will be 1 only, and from here to here again it will be 1, and from here to here it is again root 2, and from here to here again it will be root 5. So the environment around any particle must be same. Such type of the arrangement is called as the lattice or space lattice. And this space lattice is always infinite, it has no end, and the position occupied by each point is called as the lattice position, and the points that are present here are called as the lattice points. If the lattice points are occupied by the atoms, ions or molecules, they are called as the crystal lattice. Now let us try to see how many types of two-dimensional lattices are possible. Here 5 types of two-dimensional lattices are possible. First of all, doubt arises among the students that how to get these 5 types. It is so easy. These 2 are different from these 3. In these 2 cases, you can see the arrangement of the particles is in such a way that the first line represents the second line and second line represents the first 2 lines. So the arrangement of the particles, if you consider this line as a line, then the second line reflects the first line A, and third line also resembles the first 2 lines, so that A. So it is called as the A type of the arrangement. Here also the particles are arranged in the same manner. So here whatever, if you take this one as the A layer, then this must be again resembles the first layer A, and this is also again A layer. So here these 2 are of the category of A type of category, because the arrangement second layer, third layer means all the layers are same and they resembles their earlier layers. But in these 2 cases it is different. See here, if you consider this one as 1 layer, here the particles are arranged in these positions, and second layer particles are arranged in between the first layer particles. Here you can see this is the one particle, this is the second particle that is arranged in between the first 2 particles of the earlier layer, and here it is again between the 2 particles of the earlier layer, and third layer particle is in between the second layer particles, and this is exactly coincides with the first layer particle. Here also this particle coincides with the first layer particle, means this layer resembles the first layer and this layer is different from the first layer, and if you develop one more layer here, that layer automatically resembles the second layer. So if you consider this one as the A layer, this one will be B layer, again this is the A layer, this one will be the B layer. So it is AB type of the arrangement, and the same arrangement you can see here also. So in two-dimensional lattices with AA pattern we get the two-dimensional lattices, and with AB pattern we get the three two-dimensional lattices. Here now come to this point. In these two cases, here the distance between these two particles is same, the distance between these two particles. So if you take the distance as A, here it is the B, A equals to B, and the angle is 90 degrees. Here distances are different but angle is same, so A not equals to B, but angle is 90 degrees only. But these are different category. Why? Because these are of AB category type of the arrangement of the particles. So now see here, this is the A layer, this is the A distance, here this is the distance B. They are same but the angle is not same. So A equals to B but angle is 60 degrees. And in this case AB lengths are same but angle is not equal to 90 degrees. Here also AB lengths are same but angle is not equal to 90 degrees. So except this one, remaining all the cases angles are, edge lengths are same. A equals to B, A equals to B, A equals to B, A equals to B, but angles are different. The first one is called the square two-dimensional lattice. This is called as a rectangular two-dimensional lattice. This is hexagonal, this is parallelogram, this is rhombic. Now in this case, this is only about the two-dimensional structure. We are not discussing anything about the three-dimensional pattern. In three-dimensional pattern means you have to develop one more layer either behind these layers or above these points. For example, you can develop one more point here and one more point here and here one more point and here one more point. You can connect these points. Just imagine the distance are same. Now if you connect this one, so automatically you will get the square like structure. So this is called as a, if you develop one more layer behind of these layers, that is called a three-dimensional. So when you develop three-dimensional, automatically you will get the crystal structure. But without having the third line, having only two planes on a plane of paper, if you develop this type of the points, here we get the square planar, here rectangular, hexagonal, parallelogram and rhombic. Now let us see unit cell. Unit cell is nothing but the three-dimensional smallest portion of a crystal lattice which when repeated in different directions generates the entire lattice. So this is a unit cell. This unit cell is characterized by the 6 parameters. 3 are the edge lengths. A, B, C are the edge lengths, and the angle between the A and B is called as the gamma, B and C is called as the alpha, C and A is called as the beta. So a unit cell is characterized by the 6 parameters A, B, C and alpha, beta, gamma. Now let us try to see how to develop a crystal using a unit cell. Imagine, now let us try to develop the three-dimensional crystal lattice using the unit cell by repeating this unit cell. This unit cell only I am repeating this side. Now try to repeat the same unit cell in the top side. I think now you got the idea how to arrange. So this unit cell, the smallest portion, if you keep here, here and here, you got the same type of the structure. So the crystal structure means unit cell represents the complete crystal structure. So if you consider this one as a complete crystal, in this length is different from this length, just like here. You can keep one more crystal front side also. Now you got the front side one unit cell, back side one unit cell, side unit cell, top, and this side also. So unit cell is nothing but the smallest three-dimensional part of the crystal, which when you arrange in all the directions, you get the crystal structure. Now let us try to see how many types of unit cells are there. Unit cells are of two types. They are primitive unit cell and centered unit cell. Now let us discuss about each and every of these unit cells. Primitive unit cell. So in this type of the unit cell, these are very simple unit cells in which the particles are present only at the corners. So if the constituent particles occupy only the corner positions, such type of the unit cells are called as the primitive unit cells. Centered unit cells. In centered unit cells, the constituent particles not only occupy the corner positions, but apart from the corner positions, they also occupy the other positions of the unit cell. See here in this particular unit cell, the constituent particles are occupying the corner, all the 8 corners are occupied along with the center of the body of the cube. So such type of the unit cell is called the body centered unit cell. And in this case, the constituent particles occupy all the 8 corners. These are the 8 positions. These are all 8 positions. And apart from that, the constituent particles also occupied the center of each face. For example, if you consider this one as a front face. So for a front face, this is the center. And for the left side, this is the center. And for the top, this is the center. And for the back, this is the center, BA. And for the right side, this one is the center. And for the bottom side, this is the center. Means the center of all the faces are occupied by the particles along with the corner positions. Such type of the unit cells are called as the face-centered unit cells. In the case of the end-centered unit cells, these are the type of the face-centered unit cells in which all the corners are occupied by the constituent particles, but only two opposite faces, center of two opposite faces are occupied by the constituent particles. In face-centered, all the face centers are occupied by the constituent particles, but in the end centers, only two opposite faces, the center of two opposite faces are occupied by the constituent particles. Such type of the unit cells are called as the end-centered unit cell. So in all these cases, the constituent particles are present either at the center of the body or at the center of the face. Hence these are called the centered unit cells. Now 7 crystal systems. The crystal systems are of 7 types. Basic crystal systems are of 7 types. And these are further classified into 14 space lattices or Bravais lattices. Actually 32 point groups are divided into 7 basic crystal systems and 14 space or Bravais lattices. Now let's try to see how to remember these 7 crystal systems. It is very easy to remember. First of all, we should remember the 7 basic crystal systems. This is CT or HMT. Small trick is CT or HMT. C stands for the cubic, T stands for tetragonal, O stands for orthorhombic, R stands for rhombohedral, H stands for hexagonal, M stands for monoclinic, T stands for triclinic. If you are getting confused about the 2 T letters are there, then you can neglect the triclinic, because triclinic is a system, it is a completely unsymmetrical system which is very easy to remember. So you can remember it as a CT or HM. If you do not get confused, you can remember it as CT or HMT. Now in these cases, cubic crystal system, how to remember these edge lengths and axial angles? As I did here, just to write down the A equals to B equals to C in all the cases.
First cubic system A equals to B equals to C. Tetragonal, you cancel 1 from right hand side. So A equals to B not equals to C. Orthorhombic, you cancel both. A not equals to B not equals to C. Again rhombohedral are same. A equals to B equals to C. Hexagonal, A equals to B not equals to C. Monoclinic, A not equals to B not equals to C. Triclinic, all are not equal. Even axial angles also. So this is a way to memorize the edge lengths in the 7 basic crystal systems. A equals to B equals to C in the first case. Second case, right hand side you cancel it. Third case, both are cancelled. Fourth is again means the same set. This set resembles A equals to B equals to C, A equals to B not equals to C, A not equals to B not equals to C, just it resembles. Last one is anyhow not equal, all. Now axial angles, first 3 are equal to 90 degrees, alpha equals to beta equals 90 degrees, here also same, here also same. And anyhow triclinic is always not equal, that we no need to remember separately because edge lengths and axial angles are not equal. And here first 3 cases are equal to 90 degrees. So only the thing is we have to memorize these 3. In this case hexagonal, in this case you start cancelling right hand side from right hand side onwards. So alpha equals to beta equals to gamma not equals 90 degrees. So now we need to memorize only 2. Alpha equals to beta equals 90 degrees, but in hexagonal means one angle must be 120 degrees. So gamma equals 120 degrees. Here both are opposite. Alpha equals to gamma equals 90 degrees, beta not equals to 90 degrees. The simple trick is CT or HMT. And let's try to discuss about the space or Bravais lattices and total Bravais lattices. How to remember? Only first 3 cases values will be there, remaining cases almost all 1 will be there. 3, 2, 4, 1, 1, 2, 1. For every crystal system, one basic arrangement is possible, that is primitive. Whenever only 1 is there, that is always primitive. When more than 1 is there, then automatically it is body centered, except in the monoclinic. These two are different crystal systems, triclinic and monoclinic, where end centered is possible in this case. When 3 are there, primitive, body center, phase center, primitive, body center here. Here all 4 are possible, primitive, body centered, phase center and end center, because we have discussed the type of crystal systems now. So this is the way to memorize the even space or Bravais lattices and number of Bravais lattices. Hope you understand today's session. Thank you.